All right, today we are going to give a kind of a final report on the experiments we did, on the quantum mechanics experiments that we did. We're going to tell you, what we did and why we did it and how it ended up. And then after we finish with that, we're going to tell you where we're going next. And we have several other quantum physics experiments that we want to do, but we have found another project that is less expensive and probably takes about half the amount of time that we're going to do first. So the other quantum physics experiments are going to be put on back burner for a while. Doesn't mean we're not going to be working on them, but we'll just be working on them in the background. We're going to have other things going on too. And these other things are key to kind of softening up the physics community to the point that they are much more ready to talk to us and deal with concepts that are beyond the material world. And we think that we can do that. We're going to explain that just toward the end of this. So that's what this program is going to be about. So let me start with the experiments. I had an experiment that I listed on my 2016 LA talk that I wanted to do, and it was a basic physics experiment that conflicted a little bit with what the scientists said would happen. So I looked at this experiment, and you see we have the detectors on, so we're detecting, but we have the recorders of that information turned off. So there is no which-way data collected. And I said that in that case, you are going to see interference patterns. And physicists disagreed with that because they have this well, let me not go there just yet. They disagreed with that. So we were going to perform this experiment, but it turns out it has one fatal flaw, and that is physicists don't know how to do this. They can't set up this experiment. There is no way just to do the detection and not record it. Now that seems like simple. Of course you could do that, but detecting which-way data is an extremely difficult problem to do in the lab. And there is no way to just collect it without somehow interfering with the results. Every time you try to collect it, you end up changing the results of the experiment with the technique that you're using to collect the which-way data. So this experiment could not be done. This is what we wanted to do, and we tried all sorts of things. We looked at using electrons instead of photons. We looked at all sorts of things, and it just can't be done with the technology we have today. Now, maybe we'll get new technology that will allow us to do it. So we had to come up with another experiment, since that one couldn't actually physically be done in the lab. And we came up with this one. As you see, you have a source that then creates an entangled pair. Okay, now one on the bottom path that's the top path, David. On the bottom path, going through the 90,
Okay.
see, yeah, on the bottom path going through the 90, now the one on the very bottom, slit B,
Okay. Sorry. Yeah.
that's what I'm talking about. Okay, so when you go through slit B, you go through a filter, which is a polarizing filter, and that filter only allows light that has a 90-degree phase. That's called a horizontal polarization. Okay, that's where the polarization is at 90 degrees.
Or vertical. Yeah. Zero is horizontal, and 90 is vertical. Sorry.
Is that right? Okay. Depends where you start measuring
Yeah.
the
It
angle
depends where you
from.
start.
Yeah.
In
Okay.
my graph, I use the black lines here to show a vertical and horizontal, by the way.
Ah,
And this is
yes, you
diagonal.
did.
Yeah.
Okay, so we go through this polarizer, okay, and that polarizes this photon, no matter which path it takes. If it takes the upper path, it has a horizontal polarization. It takes the lower path, it has a vertical polarization. Now, the other part of these entangled twins, that's the very upper path here, okay, that then we can look at the polarization there and see, is it vertical or is it horizontal? Because of the entanglement, if the particle goes through the vertical slit A, then the entangled pair will also be vertical. If it goes through the horizontal, then the entangled pair will have a horizontal polarization. So up at that level, all we have to do is separate the vertical from horizontal, and we collect all of those that were horizontal, and those are the ones that went through slit A, and all the ones that are vertical, and those were the ones that went through slit B. So now we have which way data. Okay, that's what we're doing. Now, of course, when you use polarizers, and actually if you do almost any experiment, all the ones we know of, including the one that Scully et al. Did that you're probably more familiar with, when you do that, there's always two paths in which you can get data through the system. There's two paths. In other words, if let's say it has to be a horizontal polarization, then there's two ways to get that. You can have horizontal at 0 degrees or horizontal at 180 degrees. As far as the waveform going through it, it goes through one just as easily as the other. And what's the difference between them? A shift of pi in phase. It is a 180 degree phase shift. That's the difference between them. So because we have polarizers here, that means we're always going to get kind of a double answer, if you will. And you'll get an answer from those that were polarized at, let's say at slit A at horizontal polarization at 0 and horizontal polarization at 180, because they both pass through the filter. The filter isn't sensitive to phase. The filter is only sensitive to the direction the vectors are going, horizontal or vertical. So that's what we do. Now we can separate those two in the upper path, and we can look at all of those. We can collect all those that are vertical, all those points that were horizontal, and that then is our which way data. That tells us whether it went through slit A or slit B. So that was the experiment. Now, there was one thing that we hoped that we could capitalize on, and that is that physicists have this idea that I disagree with strongly about entangled particles. They have this idea that entangled particles that the particles themselves can entangle with all sorts of things. Everything they touch or even get close to, it seems, they can become entangled with it. Now, I think that's not a good idea, but physicists do. So there was one of these experiments where, because of this entanglement happening in the, so anywhere along there, within the BBO, within the detector, within everything it could be entangled with. So because of that, they decided that they would find a particle pattern, one lump. You see the yes or no there? Well, they said you'd get the no. And that's because this entanglement, everything's entangled with everything else, leads to the conclusion that information cannot be destroyed. You just can't destroy it. Information's always there, even if you can't access it. Okay.
If you may, Tom, just for clarity, I would just add that when we do the setup and then we agree on this is the typical way scientists do it is that in the upper path here, if we put the vertical polarizer and we get the clicks at D2, we know that the bottom photon went through slit B, which was also polarized at 90 degrees. So if it reached D1, it had to go through slit B because at the top, it also clicked at D2. In this case, we know that since we know the which way data, the interference pattern is destroyed and we get a particle-like diffraction pattern. And I just want to precise that the innovation here and what we're trying to do is what happens if we don't record. So we basically detect the which way data, but we don't record it. Like the wire, we remove the wire, so the information is never saved into a database. And that was the setup we used to try to answer this question and come back with what Tom was talking about, that the physicists say that because of entanglement, like the photon here will still be stored and saved in the detector itself. Even if it's not in the database, it will be stored in the detector.
And I strongly disagree with that concept of entanglement. The entanglement that I grew up with in graduate school was that entanglement was related to conservation laws. You know, things got entangled, and then they had to have certain values based on the values of the incoming particle. Like it came in with a certain amount of energy, then the total energy going out would have to be equal to that. If it came in with certain momentum, then the two particles going out would have to, added together, produce that same momentum, and so on. And that was the point of entanglement. So this is a kind of a newer thing in physics. By newer, I mean in the last 30 years. You know, it's been there. So anyway, there was this one experiment, and the physicist said, no, it's going to come out in a lump. And I said, yes, it's going to come out in an interference pattern. So we looked at it, and sure enough, it came out in one lump. So it meant the physicists claimed victory, that was true. It came out the way they said it did. Except when you look at that one lump, you find out that it really is not a particle pattern at all. In fact, it is two interference patterns that sum together. You know, they're out of phase, and they sum together and create this one lump. But it's not a particle pattern. A particle pattern just collects particles in a lump form. This collected particles in two different interference patterns. And when you add those two interference patterns, because of using the polarizers, you get one that's out of phase with the other. You know, that's what you say. If it goes through at 0, then it goes through at 180. They're out of phase, but both work. So you collect all of those. So indeed, I look at that and I say, no, I was right. That one lump isn't a particle pattern. That one lump is two interference patterns. And here's my analogy to that, is that think of a store window where they sell ladies' clothes, and look at a mannequin. If you have a mannequin and that mannequin looks just like a girl, I mean just like a girl, everything, eyelashes, pores, everything, it's an identical copy to a girl. But that mannequin is not a girl. It just looks like a girl. There's a big difference between looks like and is. Now, how do you tell the difference between that mannequin and a girl that looks exactly like that mannequin? How can you tell the difference? Well, you look and see what's inside. The girl has organs and blood and heart and all sorts of things going on inside. The mannequin is hollow. There's nothing going on inside. So if you look inside, you can tell what it is. So here we have a situation where if you look inside, you'll find two interference patterns. Well, to me, that says that it is not a particle pattern, it's two interference patterns. And to say that, well, it looks like a lump, so it is a lump, so it's a particle pattern, I think that the physicists needed that answer because that's what their theory projected, and I think that's wrong. So for that, I see as a win for me, for my theory. But it's not that the physicists didn't know about the two interference patterns. They're perfectly aware of those two interference patterns. All their experiments and their theory says you'll get those two interference patterns. But when they combine to form something that looks like a particle pattern, they say that is a particle pattern because their theory of entanglement requires that. My theory of entanglement does not. So that's a basic difference. So I think that was a very interesting outcome that we had from this experiment. I think it showed something important, but it's something that's very difficult to sell to the physicists because they're already committed to those two interference patterns are actually, a particle pattern because that justifies their concept of information cannot be destroyed. So anyway, that's an issue, but it's hard to argue because they just have their opinion and I have mine. So it's not something that you can really deal with too effectively. So that I thought was very interesting. Now, so that's the experiments that we did. But let me talk a little bit about these experiments. Doing quantum mechanics experiments is not easy. When I first introduced these in 2016 in LA, California, I said things like, these should be easy. It's not hard. Well, when you look at the diagram, it is easy. But when you actually try to do it, it's really hard. And I talked to a physicist who he's at the university, and he is an experimentalist, and he actually runs all the laboratories there. So setting up experiments is his thing. That's what he's been doing for a living for 30 years. And he told me that the first time he tried to do a double slit experiment, it took him 2 years to get it to work. Well, it took us 4 years to get it to work because we didn't own the lab, and we weren't able to just do what we pleased. We ran into all sorts of not technical difficulties, but administrative, problems. Yeah, university administration. We'd have somebody there doing the work, and they'd get it about 80% done, and they'd leave. Then somebody new would come in, and they'd get it to about 80, 90% done, and they'd leave. So David finally solved the problem by hiring his own person to run the experiment, getting the permission from the university for this non-university person to go in there. That was like twisting arms and begging. And eventually we got that. And then after that, within about 6 months to a year, we had it done. So we didn't have the advantage that this physicist had. He owned the lab and he owned the equipment and he had a big budget. So it took us a long time to do this.
And I would add something, Tom, just to that. On top of the university administration, it's very sensible. We're talking about individual photons sent through a bunch of apparatus and beam splitters and polarizers, and just to do one run of the experiment, it takes more than 24 hours of measurement. So this means that the physicists in the lab, they need to make sure everything is calibrated. They think it's calibrated, then they press go, they shut the light, and they go home. And this is in a university lab. So there's still, yes, it's an optic table, but there's movement around. Sometimes there's a fire alarm or whatever. So the next day, the physicists come back and look at the result, and they're like, oh, the laser was a little bit too powerful. The the polarizer or the slits were on the line for like a nanometer on the left. So we need to try it again tonight. Or the alarm, the fire alarm went off, and it created vibration that it
Yes,
created false data. So really hard, really long time. A lot of trial and errors on top of that.
that's true. And you'd have equipment that would vary. You know, the laser was supposed to be at a particular frequency, but over time it changes a little bit. So, you know, these things are hard to track down. They cost money to replace. Think of it this way. You've got a single photon going at the speed of light. That's very fast. And you're doing this experiment on a board that's about maybe, what, 5, 6 feet
Yep.
from one end to the other, something like that. So dealing with a particle that goes 186,000 miles per hour on a board that is 5 feet long, you can see there's some very precise measurements taking place here. Very, very precise in angle, in timing, and you know, you have to measure things within a few nanometers and within a few nanoseconds. So that kind of accuracy requires everything to be still perfectly. And if there's a bunch of students that decide they're late for class and they run up the hall, you know, right next to this lab, then, well, you get vibrations and it messes up the experiment. So 4 years it took us to do this, but the good side of this is not only the experiment that I showed you that is different than what the physicists say, but also this provided credibility for CUSAC. CUSAC now has bona fides for doing quantum physics experiments. This experiment will be published somewhere. It hasn't gotten to that yet because getting something ready for publication is also a lot of work. But eventually we will find a good place to publish it, and when we do, we'll let you know. So now we're on the map. CUSAC does quantum experiments. That's good. Now, there was a couple of other fallouts from this that were also very good. David did some very fine work to display the results and to help people understand the results and how the polarizers work and what happens to the light that goes into the polarizer and how it comes out and so on. So he did this, and what this enables someone to do is to design almost any experiment they want with any kind of paralyzers and so on, and then just manipulate the inputs on the software, and they'll get an output of what the result will be. So as you can see, this is our experimental setup, and you can change things. And as you change things, look on the right there. See how the result changes. And this has been put up on the web, and it's open to the public. There isn't anything out there like this. So CUSAC not only has a reputation for being able to do quantum experiments now, but it also has this site that will be used by probably every university on the planet because there isn't anything like it. So not only will CUSAC be widely known, but this will be a very big help to physics students who would like to understand quantum physics better and the experiments better, but they don't have 4 years and a couple of $100,000 to get there. But this allows them to do it all in software and see how it works. Okay, so that was another product that we created that is very important. Okay.
So this website is nearly done. Like Tom said, honestly, there's nothing like that in the world. It's going to be the best resource to learn about double slit experiments in the world at the university level, college level, and we made it so that university can use it, teachers can use it for teaching and learning, but also layperson can understand. And it's really a pedagogical buildup that we've done here, from simple polarizers to single slit and double slit to adding polarizers to double slits to entanglement and Bell states, putting all together what we learn, doing the delayed choice quantum eraser, and doing the Tom's experiment, detecting but not recording. So it's the best resource in the world. We are right now finalizing the website, connecting it to the CUSAC website. And as you've seen in my little demo, what's great is that not only you have the explanations, but you have simulators like that where you can just play with the polarizers, see the actual results, move the slit size, and you have photo equipment, the graph, the actual data you can download, and even the math. So there's nothing like that in the world. Honestly, it's I'm really proud of what we built down here. It's going to be a great resource that we put together. So just finalizing it not right now, but it should be published very soon.
So all of this that we've just described is what we used your money for. Thank you, Kickstarter. People who donated to this, this is what allowed us to do it. And we were lucky enough to get a couple of other large donations along the way, because this is very expensive and timely work. The other experiments that we plan to do are the ones where the experimenter gets to predict what a random event, how a random event will come out. You know, if it's random, whether, let's say, you get a 1 or a 0, and that's random, well, that should be impossible to predict, because that's what random means. But I can set up an experiment that actually can predict what the outcome of a random event. And that should demonstrate that these random events, the natural random events, like a decay of a radioactive source, these are natural random events, not computer-generated randomness, but actual natural radiation. So that would tell you that depending on what the experimenter knows, the actual reality shifts to accommodate that information. Well, if your reality can shift according to what the experimenter knows, then there's obviously some intelligence in that process. It's not a machine. It's taking information of what's in the mind of a human and changing the way the reality works in order to not conflict with that information. So that'll be rather dramatic, I think. It points to, it gives evidence that, you know, that there is an intelligent process behind this, that consciousness is the computer, basically, and that this is a virtual reality. It gives evidence to both of those. So that's what we're going to do next. But to do that, it's very expensive. Just one of the piece parts is like $150,000, just for one piece of equipment, $150,000. And
Tom, how does this new experiment get around the problem that occurred in the original experiment that was done?
Well, this is an entirely different experiment. There's no polarizers in here. There's no entangled particles. This is, you know, so there's nothing to interfere with the results. When you do entanglement, the way you design the experiment affects the results that you get. So you're kind of modifying what the results will be by the technology that you're using to do the experiment. And that's a hard thing. You know, quantum physics is like that. It's hard to do things without the experimenter affecting how the results come out. So, but these experiments, we've checked with some physicists. They've looked at these experiments and they say, yeah, they should work. So even the standard physicists have looked at it and agree that it should work. Now, they won't come to the same conclusions that I will come to, but I think it's pretty obvious if something that's naturally random, like a radioactive source, and you can predict it, then it's not just a random source. It's being generated. That points to it being a virtual reality. it points to something intelligent at the helm. So anyway, so we have 2 experiments like this. If we do one, then it'll be easier to do the second. It's going to be difficult. It's going to be expensive. So because it'll take probably another 4 or 5 years to do this and lots of money, we decided, actually David came up with a brilliant idea that would cost a quarter as much and would only take 2 years. And what we're going to do is we're going to soften up the scientists by delivering them paranormal experiences by the tens of thousands. You see, now if we just do it ones and twos at a time, all right, these people do, Dean Radin and his group do an experiment, and it shows that mind affects matter. Oh, that's paranormal. Fine. Well, the physicists can just, brush that away. It's just a couple of people somewhere that obviously don't know what they're doing, coming up with results that are wrong. They won't even look at it because it's just one. But we are going to work with a paranormal thing. It's called Seeing Without Eyes. And it turns out that not only is that a real thing, it's a thing that can be taught, particularly to children, very easily and quickly. And we're going to come up with a piece of software, a game, so to speak, and we're going to spread it as wide as we can. Hopefully we'll get tens of thousands, hundreds of thousands of people will get this, and they will be able to teach their children to read without eyes, with a blindfold on, or to read in a totally black room with no light, or to see what's going on in the room next door. What they're doing is remote viewing in real time. That's what they're doing. So they're just remote viewing what's in front of them now, and then now, and then now, and in real time. So it's getting data out of the database, and this isn't hard to teach. So we're going to make this attractive. We're going to make it fun. We're going to give them all the information that they need to do this, to teach their children. And our expectation is that a large percentage of these are going to work because the people actually follow the directions and whatever. And when they do, that's going to be a big deal. You're going to have all kinds of posts coming out on the internet saying, I taught my child, he can read in a black room. He can do this and that. And instead of having a group doing that, it's easily dismissed. If there's tens of thousands of people saying that they've done this, then that's hard to claim that that's a conspiracy. People all over the country, all different walks of life who are not connected with each other are reporting this same thing. And then sure enough, if these scientists have to take that seriously, because it's hard to say, well, that's just somebody's imagination. It's not. It's thousands of people's imagination from all over the world. It's happening, and here are the results. So we're going to have very strict protocols. We're going to make sure that there isn't any possibility of cheating. We're going to hire a magician who's going to inspect everything, and we've already found, obvious faults when the magician does it, using his tricks. We could look at him right away and say, he's cheating because of the way he looks, and he moves his head this way and that way because he's looking through a tiny little hole that he put down here, and he has to scan his head around in order to see things. And the people who are doing this, they don't have to move their head. And we make the letters pop up to the right, to the left. If they were looking through tiny holes, they'd have to scan, and they don't scan. So already the magician cannot duplicate what they're doing. So this will be a project, should take only about 2 years. And if it creates the splash we'd like it to create, then suddenly the world in general, scientists in particular, are going to have to deal with this idea of paranormal being a real thing. So that will help us when we go to these next set of experiments if we soften the physicists up. So that's one plan. we have another plan that's going on at the same time. And that plan is to get physicists to think about consciousness, where they actually, yes, we're going to have this quantum consciousness essay contest. And it's going to go out to physicists all over the world, and there's going to be big prizes, money that they can win if they give real interesting ideas. There will be a panel that will be set up to judge these. So it's all going to be done very, very strictly, and hopefully we'll have 1,000 or more physicists participating in this, because the money is serious enough to get their attention. Then what that'll do is it will make consciousness more of a serious subject within physics departments in academia, because they'll want to capture this money by coming up with interesting ideas about studying consciousness. All right, so that's a parallel thing going on with the Seeing Without Eyes. And we have...
And the last one is the gaming.
So yes, go ahead. Talk about that, David.
Yeah, these just mock-ups, but the idea, can basically consciousness, can intent affect matter, can affect the random outcome of random number generators. Like can will or intent could say, oh, I'm producing more ones or zeros. These experiments have been done in the past many times by the peer labs at Princeton over many years. Been done again by Dean Radin with success. He published many papers, and like peer lab, saying there's an effect when meditators and people at their will, they can affect the outcome of random number generators. But in all cases, the N is small. It's 100 people, maybe 1,000 people will participate to these experiments. So the idea here is, why not do it at scale? Why not do it with millions of people, millions of trial, to show scientists that there's really an effect that deserves to be studied? So how do you do that? And this is one of my expertise. I'm a video game developer. I have a video game company. So the idea is to create a game, and let's say a mobile game. And the idea, as you can see in that game, this is just one example. Don't stick on the drawings. But let's say the player here, an online game, needs to make a choice. Open the door. Do I open the door on the left or the door on the right? And behind these doors, it's a real quantum event. For example, we measure a particle. The spin of a particle, is it spin up or spin down? It's truly quantum, purely random. And the player makes the choice by opening, I choose left or choose right. And then we probe the particle for real using an API. We probe the particle, we measure the spin. And if it's spin up, the player gets a chest. He level ups, he gets coins, he progresses in the game. If spin is down, he sees a monster, he loses one life, he's scared. So the hypothesis is that the player will have intent to succeed, to get the prize, to progress in the game, and will not want the opposite. The idea is that we create simple games like that, or we integrate in existing video games. And the idea is that we can then probe over millions of trials very quickly. As soon as this is online, we can have millions of trials in under a month or two. And we reproduce Dean's Radin experiment, we reproduce Peer Labs experiments, but at scale, using online devices. And then again, we have evidence to show scientists all around the world that consciousness and intent can have an effect on matter.
Again, the idea is that big numbers carry credibility. If a couple of people in a lab someplace do this, it's easy to dismiss them if you're a physicist. You don't even have to bother looking and seeing what they're doing. You know it must be wrong somehow. But when you have millions of people doing this, that's a harder thing just to wave your hand and say that, well, they're all hallucinating the same thing at the same time, but these people are all over the world. They're not in one community. They're scattered across the planet, and they are being effective at modifying what happens in the physical reality with their minds. So the numbers will come with a lot of power, much harder to dismiss. So these are the projects that we're working on now. All of these projects are not all that expensive. You just have to make the software or that game. But then, as David says, he's a maker of video games, so he can manage that. And the extraocular vision that's there. We're working on that. The quantum consciousness essay. We're working on that. We have a physicist involved that understands how to do this, how to make it official, using physicists' own systems. We're not doing this outside the physics world. We're doing this inside the physics world. So it'll be the physicists themselves that will be thinking about consciousness rather than hearing the word consciousness and running the other direction, because there'll be serious prizes to win. And then eventually the more quantum mechanics experiments that we're going to do too. So all of this is kind of ongoing at the same time, but we're going to be doing the essay contest, the extraocular vision, and the protocol video games. We're going to be doing those all kind of at the same time, with the QM experiments coming up in the back. And the reason for that is the conscious essay contest and the Seeing Without Eyes and the video game, those are all going to help physicists get over their very dedicated belief in materialism, because there's going to be tens of thousands of events happening all over the world that are showing that that these paranormal things are actually real things. I think it would be hard for them to say, well, there's 10,000 people scattered all over the world, and that's mass hysteria. No, most of these people don't know each other, don't connect with each other. There's no connections between them. So none of that's going to work. So I think that will help soften them up. Then when our experiments, the more QM experiments there on the left, when we get to that, then hopefully they'll be a little more willing to look at it and deal with it reasonably, rather than just pushing it away and saying, it has to be wrong because it doesn't abide by my belief in materialism. So we want to crack that belief, at least put a crack in it. We don't expect we're going to tear it apart entirely. But if we can just put a crack in it, that will be a huge step forward. Otherwise, everything we do is easily just kind of ignored because it's done by a couple people, in one place. And they obviously just make mistakes because they're violating our belief. So anyway, that's the reason that we're doing these, and we're doing them first rather than the experiments, because the experiments will get a lot more traction after we've done the other three than they would get if we did them first. So that's what we're doing. That's what Cusack is in the process of doing. That's how the original experiment turned out. Well, actually, the original experiment was never done because it couldn't be done, because the physicists can't just measure which way data without interfering with the experiment. So that's the report. David, do you have anything extra to add to it?
No, pretty well said, Tom. Maybe just to say that the other quantum experiments will come, but like said Tom, it's complicated for many reasons. The equipment is more expensive. It takes time to collaborate with universities. A lot of administrative stuff. At least we have experience. It will be faster, but it will take longer and be more costly. While the quantum essay contest, the extraocular vision experiments, and the video game API, I would say it's 1/5 of the quantum experiment cost and complexity. So we should have results way faster with these ones at a way lower cost, while we continue working on the future quantum experiments.
Yes, so that's a good summary. Michael, you've listened to this for the first time. Any questions? You're now a representative of all the Kickstarter people.
Yeah, no, that all sounds really great and really promising. I mean, it's been a while since I've looked at those later experiments, and I'm just kind of wondering again if it's going to run into the same sort of issue where you've got a theory for how the experiment should go, but then when it comes down to the actual practical experimental practice of actually executing it. I mean, that was the problem with the first one, is when you actually sat down to do it, you had to do the experiment a certain way, and that created, the results that we got. So I'm just kind of wondering, and I'm not a quantum physicist or an experimental physicist, so I don't know how those later experiments will actually be done, and if you're just going to end up running into those same kinds of issues again.
Yeah. No, I suspect we won't run into those issues, because those issues were all created by using entanglement to measure which way data. And the entanglement comes with problems. The entanglement comes with always two ways. And then you end up with two things with 180-degree phase difference. So we have those kinds of problems. These other experiments don't use entanglement. They're more straightforward. And I think that they won't run into those sorts of problems. In fact, as I said, we have shown them to some very top-notch physicists, senior people, and they've looked at them and said, yeah, it looks like that should work. So they don't have a problem with it. Whereas when we showed them the first one, they looked at it and said, we can't do that. That won't work. We don't know how to measure which way data any other way without interfering with the experiment. So we found out that problem right away. But this time, it's not like that.
Okay, yeah, I mean, that's helpful. I guess it's just kind of the unknown unknowns about what'll actually come up when you actually try.
Exactly. And we won't know that till we actually start doing it.
And I would add that with the timing of the essay contest and bringing more scientists to the table in discussions, we'll have more eyeballs and suggestions on how to tweak the experiments to make sure that we don't run in these issues. So it's part of the essay contest idea.
Yeah. That's great. Yeah. I just had one thought about the game, David. I know that, like in the case of, say, Pear Labs or Dean Radin, a lot of the times the amount of effect that intent or will had on the outcome was generally measured to be pretty small. So when somebody is, let's say, doing a game, I know it's just a mock-up design, but if the effect is small, but then the player gets, let's say, punished in some way every time something bad happens, even though they were putting that intent into it, what will kind of keep them engaged and involved in it?
Well, it's a very good question. So
go ahead, David.
So the initial mock-ups was to, we could create a game, our own game, but this is expensive, and it will run in the issues you're talking about. Like, is it purely luck that you get most of the time? So our more recent idea that we have is to, instead of creating our own game, just integrate in existing games. So I'll give a very easy example. A lot of games nowadays are free to play. And they offer loot boxes. So loot boxes are like gift you get in the game. So you play the game, you get a gift, and you open it. It's called a loot box. And when you open it, then you have a random chance of getting a special prize. Most of the time it's like cosmetic items. So I get a hat, I get a shirt. And these items have rarity. So when a player opens a loot box, it's like a casino. So most of the time you get boring stuff like, oh yeah, an ugly t-shirt, an ugly hat. But all the players, like, they wish for the super dragon armor or whatever, okay? So the company, if we can, and this is what we're working on right now, is instead of building our own game, can we just connect with existing already popular game and just say to these company, do you want to participate in an experiment where, let's say, 5% of all the loot box you open, instead of having a pseudo-random generator, we connect to an API with a quantum random process. So the player don't even know the difference, but we can just see if when it's the quantum process connected to the opening of the loot box, do player get more like legendary item, I'll say this way, than boring items. So this way it's transparent for the players. They don't even know about it. We get the data and we don't affect the business model of the company too much because we try to on a very small subset. But the thing is that these games, like for example, Roblox, just to give one example, Roblox has 200 million players every month. I think it's 30 million daily. I'm probably wrong on that. Maybe 70 million daily. So it's a lot of people like doing stuff and opening loot boxes. There are billions of opening of loot boxes every month. So if we just get 5% of that and we can measure it for a single month, we have n equal like 100 million, which is way, way, way more than Dean Radin or Pale Lab, n equal 100 or n equal 1,000. So yeah, so that's my conclusion. But these ideas that we just presented, we're working on them. It's not clear in all the details, but that's the path we're moving along.
Well, and I'd like to mention this thing about it being small. Being small is not a problem. The reason that, Paralabs was kind of put down by the physics community because the results were small. But that is entirely nonsense. Small isn't the point. Yes, they were small. Okay, you have a random number generator and it's going to generate, let's say, 10,000 numbers. And then you're going to take the average of those 10,000 numbers. Well, you will see that after you've averaged 10,000 numbers and you do this experiment a bunch of times, they all don't have the exact same value because there's little differences, but they're very, very small. From that large a set of numbers, it's very small. So it may only be, the fourth decimal place over that you have differences. But that's not the point. The point is, if you can always, let's say you'd get instead of a 0.5 for the average, 0 and 1, you'd get a 0.499999 or a 0.500001. All right, well, that's a small difference. But the point is, if you can use your mind to always go above the 5.001, next time you do it, it goes up above 5.0001 or 5.001. You get all these things. And if you can do that 10 times, let's say, where each time with your mind you make that result be more than 0.5, not by much, tiny little bit, but it's always more. Well, that is equivalent to flipping a coin 10 times and getting ahead every time. Though the differences are small, the fact that you can make that difference fall to the positive side, say, rather than the negative side, or the negative side as opposed to the positive side, and do it consistently is huge. So the probability that you could always have it err to the positive side, even if it's in the fourth decimal place, isn't important. Yes, it's small. But if you can do that 10 times in a row, then you get, 1/2 to the power of 10. And, that then is a big, it's like 1 in, 10 million, 1 in 100 million or something that you can flip a coin 10 times and get 10 heads in a row. That's hard to do. So that's the point. Now, Paralabs was just put down, it's small, but that's because those people weren't actually looking at what Paralabs was doing. It's the consistency that isn't small. It's the consistency that is huge. Makes Paralabs came out at the very end. They had a little video and said that their, probability, you do these probabilities that show whether or not something could be just random or whether it actually has some significant connection. And that probability for Paralabs was something like 1 in a billion. One chance in a billion that Paralab could have the results they had just by luck. Well, that's not small. That's much bigger than what scientists do every day. Science is good if it's 1 in 1,000 that you could get that by by random, or 1 in 100. These probabilities, they get 1 in 100, it's good. 1 in 1,000, it's golden. That's excellent. This was 1 in 1 billion. That's not small. So the idea that the results are small is irrelevant. That was just a bunch of people who didn't bother to take a look at what was going on and just, toss it out because it doesn't follow our beliefs. They in Pear Labs invited physicists to come to their lab. They had physicists employed at their lab, and they invited others from institutions to come check out what they were doing, and they got no takers. So small isn't a problem.
Yeah, well, I totally agree, Tom. And that's part of the reason of having, let's say, trying to get millions of people involved in this sort of thing, because the outcome will be huge. Then I was just speaking mostly from the individual player's perspective, doing this, loot box or event.
Yeah.
They're flipping a coin, say 10 times or 100 times, and yeah, maybe they made it 51 instead of 50, but in the actual process of playing the game, they got what it is not very significant to that person in that small sample size of drawing that random number.
Right, but when you have tens or hundreds of thousands of people doing it,
right,
then it makes a difference. And we well do that. Those kind of probability analysis. It's easy to say, well, what would happen if it was just accident, if it's random?
Yeah.
Then how often would they get the right answer, and so on? And that can be computed. And if they do it much better than that, and they can continue to do it much better than that, we're thinking that some players will be good at it. They will have almost every place they get to open one of those boxes, they're going to be good at it because they have the knack to focus their mind on that sort of thing. And most of the players won't be good at it.
Right.
Because most people aren't all that focused when they're playing these games. Their mind might be all over the place. But if we have, out of those 100,000 players, if we have 1,000 or 2,000 of them that are good at it, then that says something, and it says it very strongly.
Well, it leads me to wonder, though, because, and correct me if I'm wrong, but I think you've said, Tom, in the past that it doesn't actually matter whether or not it's pseudo-random versus being, let's say, quantum random or truly random, just because there's still a lot of uncertainty in where that pseudo-randomness is coming from. So I'm wondering if this is already has taken place, because like David was saying, there has been loot boxes and these kind of random mechanics of getting rewards has happened millions and millions and millions of times. And there's just people naturally wanting, you say it's a weak intent, but every time, I know I've got a little son even that plays these games, occasionally with me, and he'll, open a box and just be excited and really wanting a good thing to come out of it. And that's, I think that's pretty strong intent. So I'm wondering if that's already, if the data was looked at, wouldn't it already be the case in all these games that people have affected the results to be more positive or like outside of the norm, the statistical average?
That's probably so. A lot of the games out there may be capable of collecting useful data, but if they're not designed to collect useful data, then that useful data is all falling on the floor.
And I would add, because these games are like virtual casinos is the same. It's just they don't have like a coat of paint that make it look like a fun game, but it's the same. But like they're built, like the business model is built so that the statistics follow the curve that they want, because if not, like there would be an issue. So like pseudo number generators, often like they use seeds and they use like pretty deterministic sequences. So I guess there's less uncertainty in the process. Of course, there's always like uncertainty in the process somehow, and turmoil, and the time we sometimes you look at the clock of the machine. But like if we compare these outcomes that they got in the past with their pseudo random generator, and we connect it to a quantum one where we have increased uncertainty, what's the difference with the same kind of players? And so we can compare. What's great with the experiments with n equal a million is that we can compare the actual setup with quantum setup when there's a human and when there's a bot. Because we could also have bots opening the loot boxes without any intent, and see, is there a difference when it's pseudo-random and quantum, and what's the difference with a human? And then we would have interesting results. Yeah.
Yeah. I personally don't think the pseudo-random and versus the natural random events is all that important, but as far as the outcome goes, but I think it's very important when it comes to credibility with the physicist, because they will bring that up immediately. Well, that wasn't really random, and then you're kind of stuck. Nah, you're right, it really wasn't. And what was the effect? Well, we really don't know. And then you're stuck. Then they walk away shaking their head like, yeah, you fools don't know what you're doing. So we go to that extent of using real randomness, natural randomness, because that will just shut down that one problem that we'll have. So in reality, I don't think there's going to be a whole lot of difference, but we'll find that out too. Yeah.
Yeah. Okay, great. That's all the questions I had that came up for me.
Okay. Well, then I think we have a wrap. Anything else to add to it, David?
Oh, it's good. Thank you, Michael. Thank you,
Okay.
Tom.
Well, one last thing then. Kickstart people. I hope you feel that your money was well used. We did get some good results out of it, and CUSAC certainly got on the map now as far as a scientific quantum house that does quantum physics. We've got a lot of things in process that are hopefully will make a big change in the world in about 2 years. That's kind of, we think that all these other things we're doing before we get to the other quantum physics experiments, they're only going to take about 2 years. So that's a little less than half the time it would take to do the experiments. So they will soften things up for us and make the people a little more open when we do the experiments. So that's what's going on, and that was the results of the experiment that we first tried to do, but they couldn't do it because they don't really have a way of measuring which way data that doesn't interfere with the experiment. So that's the report. I hope you feel like your money was well spent. We've had some big donations since, so that's what enables us to keep going. And if you would like to donate again, you can always go to CUSAC, cusac.org, and there's a button there for donations. We accept anything, even $1 helps. So if you want to give more to this effort, then that's the way to do it. Thank you so much for being a donor. It was that's what got us started. We'd still be nowhere at all if it wasn't for you. So thank you very much.